Okay, now for part 2, and as usual we'll begin with the if part of the IFF. So, we're talking about a coset A, first letter of the alphabet A, right? And A is the left coset generated, created by using the element x here. So A is x of h, and you have to prove, go from the right hand side to the left hand side, that if this is true, then this x belongs to this coset. All right. So we assume this, and we have to prove that x belongs to this coset A. So, alright, so we start with this. So A equals x of xh. Right? Now, element E, the unit, belongs to H. Right? That's true of any group. So the unit E belongs to H. And therefore x of E belongs to x of h, right? And xe is just x, so therefore x belongs to x of h, right? But what is x of h? Well, we're going from the right hand side to the left hand side. X of h is just a, okay, and therefore x belongs to a. Because xh is a, given that. That's the right hand side. Alright, so we've proved that x belongs to this coset. So we've gone from right hand side to left hand side. So that's the if part. Now the only if, so we start, so with the only if, you go from left hand side to right hand side. So we start with this and we have to prove that this coset is of this form, that it's the left coset of x with your h. Alright, so start with x belongs to coset A. So for the only if, so we start with x belongs to coset A. Alright? A is a coset, right? Now, if it's a coset, it will be of the form, some element of your group G. So let's say A is of this. It must be of this form somehow, right? Where this Y here is one of the elements of your group. So it's a coset, right? So it must be of this form, well, a left coset. Okay. Now, all right. Now, if x belongs to y of h, now why am I doing this? Because I'm trying to get to the right hand side, right? So I need to be talking about x somehow. So let's bring x into the discussion. All right. So if that's true, that implies that x must be of the form y of h. Right? X has to be of this form because the members of this left coset have this form. Y something, y times something, some member, or little h of your subgroup. So x must be of that form. All right. Now, if that's true, we can rewrite that. So y inverse x equals h. Let's just rewriting this slightly. Why is that obvious? Yeah, so just pre-multiply both sides by y inverse. So you get y inverse x, y inverse y, that's e, just leaves you h, so that's true. Alright. Alright, now if that's true, that means that y inverse x has to belong to H, right? Because this H belongs to little h belongs to your subgroup, right? So y inverse of x belongs to H. Now, if you write, instead of x you put y here, instead of y you put x here. So this would then be y inverse x belongs to H, okay? Y inverse x belongs to H. Therefore, YH equals XH, right? So we're now using part 1 in our proof of part 2. So this implies that XH equals YH, right? Using part 1, right? So we've got that. Right. Since XH equals YH and A equals YH, that means that A equals XH, right? Big H. Okay. Follow that? A equals YH, but YH equals XH, therefore A equals XH. And we have now proved the right-hand side. Okay, so 2 is now done. All right. So now let's do 3, part 3. So do the if case as usual first. Now, so this statement here. So we start with the right-hand side, you know, the usual thing for the if. Okay, so take two elements, and they belong to the same coset, and we have to prove that the two sets are equal. Now we're going to go through all this rigmarole again. Well, that would be the slow way. You could do it that way, but the reason there's reason in having these parts in the order that they are. In proving 3, we will use previous results. Okay, so yeah, there's a lot of good, tight, logical reasoning in this particular theorem. It's quite what's the word? Dense, I guess, right? A lot of logical steps. Makes you think. All right. Okay, so the if part. So we're starting with the right-hand side, we're doing the if, so starting with the right-hand side and trying to prove this equality of the two sets.